Good day and welcome to the first part of our discussion on integrating rational functions. So just to make sure that we are all on the same page from the starting point, a rational function, recall, is a polynomial divided by a polynomial. For example, the function x minus 9 divided by x plus 5 times x minus 2 is a polynomial over a polynomial and is a rational function. We will integrate rational functions by reaching back into our pre-calculus tool bag and utilizing partial fraction decompositions. But before jumping into partial fraction decompositions, let's look at a motivating example. Now note, in its current form, this appears to be a rather difficult integral for us to evaluate. There is no obvious substitution. It doesn't appear well suited for integration by parts. It's not a trigonometric integral, and it doesn't look like a trig substitution would necessarily apply. So what we're going to do is manipulate this algebraically. And what I want to note, and it's not obvious at all, is that if we rewrite this quantity that's in the top, x minus 9, I could write that as 2 times x minus 2 minus the quantity x plus 5. And we'll see where I'm going with this in a moment, but you could double check the algebra. Once we've rewritten it, note we can break this up into two separate fractions over this negative sign in the numerator. So the first term we would have is the 2x minus 2 divided by the denominator. And in that case, those x minus 2's would very conveniently cancel and leave us with a 2 over x plus 5. Then we'll be subtracting away a second fraction, which is formed with x plus 5 divided by the denominator. In that case, the x plus 5's very conveniently cancel. And once we have it in this form, immediately we have an antiderivative. This would be 2 natural log absolute value of x plus 5 minus the natural log of the absolute value of x minus 2 plus c. And from what we've done here, the algebraic method or approach is not clear, but we will have a very methodical way of going about this in a few minutes. But language-wise, let me just note, when we have rewritten our rational function in this current form, this is something that we call a partial fraction decomposition. And I will almost always abbreviate a partial fraction decomposition as PFD. And let me give you a reminder. I know it may seem as though it's been quite a while since we've had pre-calculus, but in our pre-calculus course we spend some time talking about partial fraction decompositions. Partial fraction decompositions are an algebraic tool or technique that allows us to take a rational function and breaks it up into simpler pieces that we're adding and subtracting together that we can integrate much more efficiently. So our goal for this current video is to go back to this pre-calculus topic of partial fraction decompositions and remind ourselves of the general procedure that we would use to find a PFD of a rational function. And luckily for us, there's a nice, well-defined procedure that we will follow. So we start off with a rational function. In this case, f of x equals p of x over q of x. And remember, because it's rational, that means we have a polynomial over a polynomial. The first thing we need to check is compare the degrees of the polynomials p and q. If the polynomial p in the numerator has a degree bigger than or equal to what's in the bottom, we will call f an improper rational function. And if we have an improper rational function, you would first need to do a polynomial long division before getting to the PFD. And this is something that we are going to hold off on for a future video. But for now, let me just note with a quick example, a function such as f of x equals x squared minus 1 over x minus 7 is an improper rational function because the degree in the top is 2, which is larger than or equal to the degree in the bottom, which is 1. Now the ideal case is when we have a proper rational function. So a proper rational function, the degree of the polynomial in the top would be less than the degree of the polynomial in the bottom. And in that case, our approach to doing a partial fraction decomposition is to take the polynomial in the denominator and factor it into terms which are linear or irreducible quadratics. And what we mean by an irreducible quadratic is it's something that does not have any real roots. So it doesn't factor further into two linear terms. And once we have this polynomial q of x in the denominator completely factored, the factors of q of x will tell us what terms and how many terms will appear in our partial fraction decomposition. So let's begin thinking about the linear terms. If q of x has a linear factor, every power of this linear factor is going to correspond to a term in our partial fraction decomposition. So if ax plus b raised to the nth power is a factor of q of x, then the PFD will contain the following m terms. We'll have something over ax plus b, something over ax plus b squared, all the way up to something over ax plus b to the nth. The idea being that each and every factor of q contributes to a term of our partial fraction decomposition. And these different powers of ax plus b are all different factors of q. And then we balance them out by putting a constant above. I will just arbitrarily refer to these as A1, A2, all the way through AM. So in this case, the A1 through AM are constants. And in a moment, we'll get to some nice concrete examples. I know it seems a bit abstract or very general at first. So now on to the quadratics. Each quadratic factor of q is going to contribute terms to our partial fraction decomposition. And similar to what we saw above with the linear factors of q, if you have an irreducible quadratic factor of q which is raised to the nth power, it will contribute n terms to the partial fraction decomposition. And the terms will be as follows. There's going to be an ax squared plus bx plus c term. There's going to be an ax plus squared plus bx plus c squared term, all the way up through an ax squared plus bx plus c to the nth power term. So one term corresponding to every power less than or equal to n. And because they are quadratics now instead of linears, we balance them above with a linear term. So we'll say b1x plus c1, b2x plus c2, all the way up through bnx plus cn, where in this case, the b1 through bn and the c1 through cn are all arbitrary constants. For any given example, we will want to first write out the form of the partial fraction decomposition. It will involve arbitrary constants. Then algebraically, we solve for those constants. So let's work our way towards some concrete examples. When it comes to finding the PFD of a rational function, the first step is always going to involve writing out the form of the PFD. So let's go through a couple examples, and I think seeing something concrete will definitely help formalize what we had on the previous page. So looking at our first bullet, notice this is a proper rational function. The degree in the top is 3, the degree in the bottom is 6. So smaller degree in the top than the bottom. We have a linear term x, a linear term x plus 2, which is squared, and a linear term x minus 1, which is cubed. So each and every factor of the denominator contributes a term to the PFD. So there will be a term for x, x plus 2, x plus 2 squared, x minus 1, x minus 1 squared, and x minus 1 cubed. So each and every factor of the bottom contributes a term. And whenever that term comes from a linear factor of the denominator, which is all we have in this case, we balance it out with a constant. So A, B, C, D, E, and F. This is what we'd refer to as the form of the partial fraction decomposition. And now that we've seen what we are looking for, I would like you to pause the video and write down the form of the PFD for the next two rational functions. So hopefully you've paused the video and you've thought about this for a few minutes. In this second bullet, we have an irreducible quadratic and a linear term. That means that our PFD will contain two terms, but how many constants? Let's see. We have one term corresponding to each factor. So there's the x squared plus 1, which is kind of a standard form for the irreducible quadratic. And we have x minus 3. Above the irreducible quadratic, we balance it out with an ax plus b and use just a single constant above the linear term. So there will be two constants corresponding to each term coming from an irreducible quadratic and a single constant corresponding to each term coming from a linear factor. Similarly, if we look at our third bullet, we will have three terms. The first term corresponding to x squared plus 1, then x squared plus 1 squared, and one term for x minus 3. Our constants of balancing this out above would be an ax plus b, cx plus d, and e. And the idea now is if you wanted to integrate one of these functions, maybe pick the middle example. If you knew the constants a, b, and c that made this true, you could break it up into three separate but extremely reasonable integrals to evaluate. Which leads us into our next topic of discussion. How do we solve for these constants? Let's go ahead and look at a nice concrete example and see if we can find the actual partial fraction decomposition. So our first step is to factor the denominator. X squared minus 5x plus 4 very quickly factors into x minus 4, x minus 1. The form of this partial fraction decomposition is going to contain two terms. There will be one term corresponding to each of these linear factors. So an x minus 4 and an x minus 1. We balance a linear term out with a single constant. This is what we would refer to as being the form of the partial fraction decomposition. What we now need to do is solve for a, and B. And the observation that I would like to make is we are guaranteed that we can find A and B, and the A and B values are numbers that make this true for every value of x. So we need to find / solve for A and B. But the key observation is they work for all values or any value of x. And with that in mind, we're going to maybe pick a couple intelligent choices. So first, if we think about this purely from the algebraic perspective, this appears to be difficult because we're dealing with fractions. If we take the denominator on the left-hand side and we multiply through by it, it becomes substantially simpler. We'd have an x plus 5 on the left. In the first term on the right, the x minus 4's cancel. And in the second term on the right, the x minus 1's cancel. Now, if I want to solve for A, what is a value of x that I can substitute in to make the B term vanish? 4. Note if we substitute in x equals 4, the left-hand side is 9, and the right-hand side is a times 3 plus 0. So immediately we know a must be equal to 3. Similarly, if we would like to solve for b, we need to think of a value to substitute in for x to make that a term vanish. X equals 1. If we substitute in x equals 1, the left-hand side is 6, and the right-hand side is 0 plus b times minus 3. So b is minus 2. Let me note that there's also an alternative way to go about this. If we look at the equation we have on the left, we could go ahead and just expand everything out on the right. So expanding the right-hand side, we would have an a plus b times x, so kind of combining terms while we're at it, minus a minus 4b. And an observation that we can make is we have a first-degree polynomial equal to a first-degree polynomial. And the only way two polynomials can be equal is if each and every one of their coefficients are equal. That is to say, a plus b in front of the x must be equal to 1, and minus a minus 4b must be equal to 5. And that gives us a system of two equations and two unknowns. Which you can solve to determine a and b, and you would not surprisingly find a is 3, b is minus 2. Note, whenever we only have linear terms, this first method works wonderfully. When we have more than just linear terms or linear terms raised to powers, then we're going to have to somehow set up systems of equations, something we will certainly encounter in future examples. But be aware that there are multiple approaches. We've been asked to find the partial fraction decomposition. It's really important to kind of summarize our solution. So we have x plus 5 over x minus 4, x minus 1 is equal to a over x minus 4 plus b over x minus 1. And lastly, what I would like to note, really kind of just as an afterthought, is once we've done this PFD, we can very quickly very efficiently integrate this function. So simply note, if we want to integrate, we can rewrite the function in terms of its partial fraction decomposition. And each individual term can be anti-differentiated rather quickly. So for now, the newer part of the problem, at least in the sense of something we haven't done all that recently, and the more difficult part of the problem is going to be the partial fraction decomposition. But as we go through and practice more and more of these examples, they will become quicker and more efficient. And we will continue on with more examples in our next video. So stay tuned, take care.